This is not about synthesis where you produce a nanomaterial and put it in a vial or bottle, okay? But this is about synthesis on a substrate, wherein you want to have the given nanomaterial in a definite pattern. Patterning is important if you want to make electronic or magnetic optical based devices. So I'm not going to get into the device functioning aspect. I will only tell you how to bring in material, a simple metal, oxide, or even compounds of very stoichiometry, involved stoichiometry, how to bring in 3-component, 4-component kind of systems. What are the paper, right? And these ink molecules, ink particles, whatever they are, they just get embedded in the cellulose matrix. Because they have a color contrast, you are able to read the pattern. And so this is one type of lithography. But of course, as you realize, you're not truly working at nanometer, but you're working at several hundred micrometers. When you take a gel pen and read across its body, it says how sharp is the tip, right? So they say 0.5 mm, 0.2 mm gel pen. What it means is it is doing the ink delivery with such precision. But we are talking about lithography at a much different length scale, much lower length scale, and that is nanometer. So how do I design a pen wherein I can use the pen and do some direct writing, wherein these letters, the feature size belongs to nanoscale. So that is the topic today. And as you write, you want to write with a given ink. It could be simple, the kind of ink you're using for the pen. These are typically colloidal dispersions. Or you want to use molecular ink, or you want to use a bio ink. It may be DNA solution you want to write. I don't know. So how to go about writing any given ink on any given substrate. And with a control over length scale, typically few nanometers to few tenths of nanometers, and perhaps maybe up to a micron. Or at times you may have to really fill the ink over a large region uniformly, and that is also comes under the lithography recipe. The other way of doing it is, instead of direct writing, you may want to arrange a stencil and just paint it over, and then take out the stencil. You will have the impression coming up. So in this case, the ink is all over the place except the region what you want to create, so-called the feature. So this is just the replica of what is being done here. And another way is to actually create a stamp with replica feature like this, and you pick up the ink only in these regions and stamp it. When you stamp, you will be passing on the ink which is coated on these raised impressions raised impression onto the substrate, and that's how you create a given pattern. I can't think of anything different from these three principal modes of writing. If you do think, probably you can write an essay in the end and give it to your convener. So lithography is all about these three modes, and only what changes during the lithography process is there are a number of lithography methods, recipes, and what goes on changing is basically the ink, the paper, pen, brush, mask, stamp, whatnot. The tools keep on changing, right? And that's how the different lithography methods have evolved, whether we write at the macro scale or the micro scale or even down to nano scale. The language remains the same, just that you enter into the regime of nanoscale. You will have to be dealing with sophisticated tools. Not always, but most often. So we're talking about ink. Unlike the ink where the colloidal dispersions what we use, or the gels what we use, here for nano patterning we use photons, electrons, molecular ink, whatnot. And then paper could be, people still use cellulose paper for nano patterning. There are some results in the literature. But commonly supports like silicon dioxide on silicon with a given thickness. Typically SiO2 would be of the order of 100, 200, 300 nanometer, well-defined thickness of the SiO2, because in the device it serves as a dielectric barrier, okay? So its thickness is important. And then polymeric substrates and polycarbonate, for example. The CD, DVD material is polycarbonate, so you can see the fine grooves which are there around. It's all coming from patterning into the polycarbonate substrate. And you will have a number of these so-called resists. I'll be using this term quite often. A resist is something which is sensitive to the ink, the photon beam, the electron beam, whatnot. It undergoes chemical changes, it responds, and it's called resist. And the pen can be a focused photon beam, focused electron or ion beam, or even just a sharp tip. When I say sharp tip, it could be STM tip or AFM tip. Okay. Then brush, I'm just using the common terminology and trying to convert the whole thing into nano patterning language. The brush, what we use commonly, is equivalent to, in the nanoscale, scanning an electron beam or ion beam. Okay. Similarly, mask, it could be high resolution stencil made of metal or a transparent sheet. And stamping tools are essentially made up of some elastomers like PDMS, not the common rubber, okay? Because common rubber doesn't offer good resolution. Well, there are variety of very diverse methods of lithography, and I have classified them into 5-6 major categories. Can someone go and advise these people to reduce the noise? So they think it is Sunday, but we are working. So there are different types of lithography methods. Optical lithography, which obviously makes use of light beam, and then charged particle beam lithography, electrons or ions, and again here we have optical, but in a different sense. Soft lithography makes use of stamps. Then these are some air-water interface techniques. Then of course scanning probe lithography techniques. Let me spend a minute or two detailing out on each one of them. When you talk about optical lithography, you have actually a broad beam of light which is shining from the top or from bottom in a given direction, and then you are using it to pass through a given mask. Actually the mask contains the kind of pattern what you want. So the light is passing through that, and the kind of resolution you want to reach would seriously depend on the wavelength of this light. I think we'll go through the details in the next slide, but you can see here light of different wavelengths is used, even down to X-ray. Okay, just to increase the resolution of the pattern. And when it comes to the charged particle beam, people use electron beam lithography, but if you want fast chemical changes or rather robust chemical changes, one can be using even ion beam, like helium ion beam. Then there is yet another class of optical lithography method which does not use light in the common sense, which is all far field, light in the near field, right? So when you have a light source, a scatterer for example, if you get pretty close to it, if you're standing within a few nanometers from the light source or a scatterer, the way the light behaves pretty close to the surface is different from when it is propagating in free space far away from the source. Okay, we all use light standing far away from it, but if you go very, very close, light behaves in a very different way, wherein it is not restricted in terms of the diffraction limits, and that is what is being exploited when creating near field lithography. And then on soft lithography, there are in fact a bunch of techniques. I have only listed out a few of them. When it comes to soft, it is all about elastomers, creating stamps, and then creating patterns. And you can't be using the common rubber, because the common rubber, the particle size is of the order of few microns, and it doesn't permit you to stamp something. You won't get the resolution you want in terms of nanometers. While using the stamp, micro contact printing is the way you put a seal, and then replica molding is a variation, micro transfer molding, and molding in capillaries, solvent assisted micro. Bunch of these concepts we'll be using as we go on. I'll show you examples and how fine patterns can be derived using soft lithography. In Langmuir-Blodgett lithography, you essentially have an amphiphile or oil molecule which is forming a film on water, and because you cause some changes in the pressure as you apply surface pressure, you may end up having some undulations in that film. Okay, those undulations are exploited in creating patterns. So these are very specialty techniques, and in fact literature is filled with such specialty techniques. Today is not the time to get into details. Scanning probe lithography is divided into STM based and AFM based. You know the techniques, right? So STM tip, a metal tip itself, can be carrying a potential, electric potential, and it can cause some chemical changes on the substrate. We will be taking some examples of that kind, but in relation to AFM we do more, and in the AFM we have you can actually mingle light with atomic force microscope. This is the best tool to deal with. In fact, if you have optical fiber itself turned into AFM tip, and the fiber itself has the light pipe, then you will have the light emanating out. Anyway, you take the AFM tip pretty close to the substrate, right, in order to sense force. So there you can use the optical field, and that is not far field but near field, wherein you are essentially free of the diffraction limit, and you can actually achieve much higher resolution patterns. And then there are grafting, shaving techniques, nano imprint, of course we are going to deal with, and dip pen we are going to deal with. So there are plenty of techniques available, depending on what kind of pattern, how large area you want to do, how fine you want to do, how specialty, what kind of specialty ink you want to bring in. Depending on that, variety of techniques are available. But before you practice any kind of lithography, you have to worry about the environment around you. Okay? If I start patterning in this particular hall, if I'm trying to do, for example, 10 nanometer pattern of a molecular ink or something, and as I go on writing, I will have a lot of dust particles coming over and decorating the substrate, right? Where do I go? It's like, you have in this room dust particles which are measuring 10 micron, okay, 1 micron, 0.5 micron, even 100 nanometer. All are big features compared to the pattern what I'm writing. So if I draw 10 nanometer line, is as good as bringing in a big stone and keeping next to it, or dumping something on top of it. So the pattern what I'm writing will not serve me eventually in a given device, because its properties will be altered by the dust itself, right? So you need to have a control on the dust, okay, in the environment where you are creating the patterns. And that's why you cannot be doing it in the ambient like this. You can hardly do patterning in the ambient. You will have to be, more or less all the time, you have to be doing patterning in the clean room environment. So what are clean rooms? We'll spend just a couple of minutes. Clean rooms are clean rooms, actually, the term itself explains. But there is, of course, some terminology, some units are associated with that. So you're essentially measuring number of particles of given size in per cubic length, whatever. So meter or feet. And this is how they look, clean rooms. And here even the floor would be made in such a way that it won't attract dust, right? Dust is attracted whenever you have a surface which is carrying charges. So dust tends to settle down on surfaces, not just by gravity, because they are more often they are Brownian particles, but they settle on surfaces which are carrying surface charge. So if you can drive away the surface charge, dust will not be there. I mean, at least it can be avoided. That's why the flooring is made up of electrostatic layers which conduct away the electricity. There is nothing like stored charge on top, so they can be devoid of, at least as a source of collection of dust. So the specialty flooring and everything around there is made of something wherein dust accumulation is prevented, avoided, including the layers, including the clothing what they wear. All that is electrostatic, anti-electrostatic. Okay, so charge is driven away, and typically it's all with yellow light, because the kind of these photoresist, electron beam resist, what one would be using, they are sensitive to the other wavelengths in the visible region. So yellow is considered safe, and so most clean rooms operate with yellow light.